Hello. We're going to talk today about the word significance. It's one of those words that get thrown around a lot because people think they know what it means. And generally speaking, they're right. We talk about our significant others or something being a significant moment in our lives. In these contexts, significant is a synonym for important or meaningful. And in everyday speak, that's great. Keep using it that way. In statistical analysis, however, significance is something else. It has a specific meaning, a statistical meaning. It's one of those words that needs to be used with precision because if we're not careful with how we use it, we can misinterpret or even misrepresent our results. And that's not good. So, what exactly does significant mean in a statistical setting? To answer that question, let me tell you a story. Okay, here we go. Imagine that you own a taco truck. You're thinking about changing your salsa. You've been using the same one for years, the same salsa for years. And before you do anything drastic, you need to know which one is better, the old salsa or the new salsa you're thinking about changing to. You can't afford to keep making them both, so it needs to be one or the other. And being the conscientious taco truck owner that you are, you need to pick the one that your customers like the most. Fortunately for you, you're well trained in the ways of research design. So, you run an experiment. When each customer comes up, you flip a coin. Heads, they get the old sauce. Tails, the new one. This is your random assignment, assigning them to control group or experimental group. And after they eat, you ask them to fill out a brief 4-point Likert scale survey that rates how well they like the salsa. This is, did you like the salsa? 1, strongly disagree. 2, disagree. 3, agree. 4, strongly agree. Something like that. So, you do this for a couple days, and after 2 days, you have 200 surveys completed. 100 people who ate the old salsa, that's your control group, and 100 who ate the new salsa, that's your treatment group or your experimental group. With trembling hands, you enter the data. The computer does what it does, and you have your results. The average score for the control group, the old salsa folks, was 3.5. It's pretty good. But the average score for the treatment group, the new salsa folks, was 3.65. Looks like this. That's even better. And on the strength of your data, you immediately donate all of your old salsa to charity. The statistical gods have spoken. People obviously prefer the new salsa, and you'll give them what they want. And on the surface, it seems pretty straightforward, right? The new salsa, right here, scored higher, and on average, it's an open and shut case, right? 3.65 compared to 3.5. This is the one they like the most. It's easy, right? Not necessarily. Because here's the thing. When you're comparing two means or averages, one will almost always be higher than the other. For example, I could randomly divide you as a class into 2 groups and test your knowledge of Civil War weaponry. One group would probably have a higher mean than the other. However, that doesn't necessarily mean that the 2 groups are actually different. Even though there's a variance in your scores, it doesn't mean that you represent 2 different populations, a population of those who know about old weapons and those who don't. It's possible that the difference in your scores is due to chance. There's always the possibility that whatever variance we observe is due to plain dumb luck. Random selection will always yield some random variance. So even though one group scores higher, that doesn't necessarily mean that they are in fact 2 different groups. The question isn't whether or not there's a difference between the scores, because like I said, there's always, or almost always, a difference between scores. The real question is whether or not that difference is due to chance or due to something else. Did the new salsa score higher because it really is better? Or was the difference in the scores nothing more than a blip of randomness? This is where significance comes in. When we ask about significance, we're really asking this question. Given the number of people that I surveyed about my salsa, and given the distribution of their scores, what are the odds that I would see this big of a difference between their scores if the new salsa didn't actually taste better? Let's approach this from a different angle. If I divide you into 2 groups and test you on Civil War weapons, I expect to see a difference between the 2 scores, the group scores. Randomness more or less assures me that I'm going to see that. But given how many of you there are, and given the nature of your data, is randomness alone likely to produce a difference as large as the one I'm seeing? Or is something else going on? Does one group actually know more than the other one does? Significance can answer that question for us. Sort of. Actually, well, kind of. Significance tells us the likelihood of seeing this particular difference in scores due to randomness alone. So let's take it back to the taco truck. The two groups had different scores, so you remember right here. Old salsa, 3.5. New salsa, 3.65. Obviously, one group has a higher average. But, as we've just discussed, that difference might be due to the quirks of randomness. So, you run a follow-up test. A special kind of test that compares the means and calculates the likelihood of these differences occurring due to random chance. This test takes a few different things into account. It takes the number of subjects that you have in the study, and it looks at the distribution of the data. For example, do people score really low and really high, and that creates an average here, or all the scores kind of centered around that average. And after all is said and done, the test gives back to you what's called a p-value. There are a few intermediate steps here I'm skipping, so you statistical purists out there, please forgive me. Eventually, you get what's called a p-value. For our purposes, a p-value can be read as a percentage. So, for example, a p-value of 0.456 would mean there's about a 45% chance that the differences between the means is due to randomness. And there's a corresponding 55% chance that it's due to something other than randomness. Do you remember how this math works? 0.45 is 45 parts out of 100, so it's 45%. Let's look at another example. Similarly, a p-value of 0.03 means there's about a 3% chance that the difference between the means is due to randomness, about a 97% chance that it's due to something else. So, you have your taco truck. You run the appropriate tests. You get a p-value of 0.07. The old salsa scored a 3.5. The new salsa scored a 3.65. There is a difference between the means. The p-value tells you that there's a 7% chance that that difference is due to nothing more than randomness. But there's a 93% chance that it's due to something else, like possibly that the new salsa really does taste better. Now, to be clear, the p-value does not tell us exactly what that something else might be. This is a very important point. The p-value tells us there's a 93% chance the difference we see is due to something other than randomness. It might be better tasting salsa, and it might not be. There might be some other variable that we didn't control for. But that's really a question of research design. The statistical question has been answered. There's a 7% chance that the difference between the means is due to randomness. So, which salsa do you go with? The new or the old? This is where things get sticky. How much of a risk can you live with? Are you willing to make a major change to your business if there's a 7% chance that what you saw was nothing more than random difference? How low would that number have to be before you were comfortable making a decision? 5%? 1%? In educational research, we're generally comfortable with a 5% chance. We could compare, for example, two groups of students using two different curricula. The group using the new curriculum scores higher on the test. Is this just a random difference? For educational research, when we crunch the numbers, let's say we get a p-value of 0.047. That tells us that there's less than a 5% chance that the differences on the test scores were due to randomness. And so we're usually willing to say, yes, let's buy the curriculum. Is it possible that the differences are just random? Yes, there's always that possibility. But in educational research, we can live with a 5% chance of being wrong. In medical research, however, the standards are higher. They generally require a p-value of less than 0.001 before they'll approve a new drug. Lives are at stake. And before they have people spend thousands of dollars on new cancer treatments or risk serious, devastating side effects, they want to make sure that there's less than 1 chance in 1,000 that the differences in cancer survival rates they've observed were not just random. They need to be as sure as they can that what they saw was not random variance. Means will always be different when you're comparing two groups. However, if the likelihood of them being as different as they are is less than 5%, in other words, if p is less than 0.05, we say that there is a significant difference between the means. There it is. The p-values for differences between your SALSA scores was 0.07. By the standards of educational research, that would not be significant because p is greater than 0.05. The odds that the differences are due to chance are just too high. Now, for choosing salsa in a taco truck, that might be okay. For working with students, not so much.